So, what's the first thing that's the problem?
The same denominator.
Or the denominator issue.
The denominator issue. So, we can solve that by either
Making it 2x over 2.
making all the denominators the same,
Oh, that.
correct? Or getting rid of the denominators, right? So there's two different ways to do that. We have to find our least common denominator, which would be
Oh, this thing.
6, excellent. Okay, then so we either have to make this one 6, this one 6, and this one 6, right? So how do I make 2 6? Times 3, so the top has to be times 3. How do I make this one 6? Times 6 times 2, right? Once they're all the same, we can get rid of the denominator. It works out.
15x equals 2.
Yeah. 15x equals 2. 2 equals x equals 2/15.
You got that right. What number is that?
It looks like a 45. Is that a 1?
Wait, what question was that?
21?
Now it looks like a 1.
2 over 45.
So I thought it was 4. Okay, so the second way to look at that is basically just doing what we did in the first place, saying my common denominator is 6, right? So 2 goes into 6 3 times, that gives you the 9, 6 times x, 3 goes into 6 2 times. So basically you don't do the bottoms and you just get rid of it. Any other ones? Any questions from our work that I signed? Your homework. The exponent review or the simplifying radicals? Okay.
I was good at those.
What?
I'm good.
Good. Okay. Radicals. So make sure that you have out your review of radicals that I passed out last week. So we're going to finish going over this. And then Nazarene handed you guys a new one called rational and irrational numbers. So this is going to be sprinkled in amongst it. Okay. So what we learned last week was radicals. A radical is the opposite of what?
Square root. Or,
Not necessarily a square. Exponent. Excellent, Hadrian. It's opposite. Hi. It's the opposite of all exponents, right? So we end up with PERMDAS instead of PEMDAS so that they mix together. Okay, so we have a radical. If it doesn't have a number, remember this is called an index. If it doesn't have a number, we assume that it is the number 2, right? It's a square root. Otherwise, it has to have a number. It has to say the 3rd root or the 4th root or the 8th root or whatever. You're not really going to work with those things. Okay, what did we say the simple way to think of with this root, this index here? It tells us our exchange rate, or it tells us how many of the same number we have to have underneath, correct? So if I have the square root of 8, the first thing that we do is we break it into
2 and 1.
factors.
Oh.
Yep.
Yeah.
So we want to try to find a perfect square, or we can break it all the way down into the factors. My index tells me how many of the same number, so I have to have groups of 2. Here's a group of 2. When I have a group of 2, it's allowed to escape. So you can kind of think of it like an escape room or getting out. So here's a group of 2. It gets to go to the outside. It escapes. It doesn't escape as a 4. It escapes as the actual number, right? So we have 2 on the outside. And what got left? The lonely only. Square root of 2. So 2 square root of 2. if I have the cube root of 8, so we're back to our prime factors, it tells me I have to have groups of
3.
3. I have to have groups of 3. Here I have a group of 3.
This would be 2.
I have 3 2s, so they get to escape. So the answer is just 2. Do I have anything left on the inside? No, nothing left on the inside. Okay, so this, I'm gonna pull something off of this rational and irrational one right here. Okay, when you have, like this one, cube root of 8, it equals 2. It ends up with a regular number. Okay. This is a rational root. Okay, so we have 2 different things. We have rational and we have irrational. Who has ever dealt with an irrational 2-year-old? Okay, do they make sense?
No.
Okay, can you explain why they need to get their shoes on because you're taking them out to the park? No, they just want a popsicle. They're like, ah! Right? Okay, you cannot reason with an irrational 2-year-old. So when we're looking at rational and irrational numbers, way back at the beginning, we did that circle. It looked like a galaxy chart, right? We had our real numbers, real number system. So we have our counting numbers, our whole numbers, our integers, our real numbers, and then we have irrational numbers. So these are all rational. And we have our irrationals, right? What's interesting to think about is that irrational actually comes from the word ratio. So that's what we're really looking at, is that a number has to be written as a ratio to be irrational. So 4/7, okay? Or 4/9. So anything over a 9 is a repeating decimal forever, okay? So while it doesn't terminate, it is the same repeating number, okay? It's still a rational number. You can write it as a fraction, as a ratio. Ratio is another word for fraction. Okay, so on your notes, if you want to fill in, rational numbers are any numbers that can be written as a fraction, where it's a over b, and b cannot equal 0. So your bottom number there cannot equal 0. Okay, so this is a quick review on rational and irrational numbers. Okay. An irrational number, it's crazy, it's all over the place. Okay, it's going to be a squiggly. It cannot be written as a ratio, which means it cannot be written as a whole, any number, an integer over an integer, a over b. Okay, it does not terminate, it does not repeat. Who can think of the most famous irrational number? Pi. Excellent. It goes on and on and on. It never terminates. What if I have 0.599 and it continues to go on? These can often be, or 3.59, can be a little tricky sometimes because you're like, wait, but it started with these numbers and then now it's repeating. So if you were to graph it, it might look like this, and then it repeats. Once it starts repeating, it's still a rational number, okay? Irrational numbers are all over the place. So it doesn't matter if it starts repeating after the first one or the last one, okay? So when we are looking at rational, so pi is an example of an irrational numbers, okay? Perfect squares. So if we have our counting numbers, 1, 2, 3, 4, 5, 6, the perfect squares of them would be 1, 4, 9, 16, 25, 36. Correct? Because that just means, what does a square mean? The number times itself, correct? Okay. So perfect squares, when we are looking at square roots, will always be rational, right? Because we're just going back and forth. But if I end up, so we're gonna do the next one, we've got a square root of 12, okay? We break it down into its factors. I've got 4 times 3. 4 is a perfect square. So I can bring its root out. So I've got 2 square roots of 3. Now we have an irrational root, okay? If it was just the square root of 4, it would be rational. But anytime we get left with a root left, then that's irrational, okay? Now number 6, its numerators can include the number 1, but the denominator does not.
Did you say?
Sorry, 0. What?
Did you say 12 is
12 is irrational.
irrational?
Irrational.
Okay.
Because it's left. It has something left that we can't solve. Okay? So our square root of 3 doesn't have even square root of 2. They don't have exact answers. We can approximate them. You can type this into your calculator, and your calculator will go till like 10 digits, and you will get a bunch of numbers, but it will never repeat. It will never terminate. It just goes on and on. It's irrational. Okay, so it's crazy all over the place. Okay, you cannot write it as a ratio.
So do we write those numbers as the examples of perfect square?
So in the underneath, it gives you a list. So let's go through those together. Hey, Nathan, point 8. What would you think about that one? Rational or irrational?
Rational.
Rational. Perfect. Okay. Hadrian, square root of 64.
Rational?
Rational. Yes. Why?
Because it is rational.
Okay, let's look at that one. Square root of 64. 64 is what?
8 and 8 goes to 4, 2, 2, and
It
yeah,
just keeps going.
yeah,
Okay.
a
so
lot of
here-
2s, which equals like
Okay, and I need groups of 2, right?
it's 8.
So there's one group, there's one group, there's one group. Or we could have stopped back here and said, oh, I only needed 2 groups. I have 2 that are the same. So you can stop at the top. You don't have to work all the way down if you don't want to. All I'm looking for is groups of 2. So the moment I get a group of 2, I can pull it out. Okay? So the answer is 8. So it's rational. Doesn't have anything left over. Okay? Micah, 0.
Rational.
Rational. Okay? Nazarene, square root of 32. Okay, let's look at that. Square root of 32. 32 is what? We're going to find a perfect square. 32 is 2 times what? 2 times 16. 16 is a perfect square. I know it's 4 times 4. So there's my group of 2. So the group of 2 gets the lead, so it's 4 square root of what's left? 2. Did I have something left over? Yes. So it's irrational. Square root of 32 is irrational. Okay. Negative 19, Nathan.
Rational.
Rational. Hadrian, negative square root of 100.
Rational?
Rational. Yep. What's the square root of 100? 10. Doesn't matter if it's negative or positive. Okay. Micah, 2.3434443444.
Rational.
Irrational.
It keeps going.
It keeps going and it's repeating, but it's not the same repeat. So the first one, it has 1 4. The second has 2 4s. The third has 3 4s. The fourth would have 4 4s. Okay, so it's continuing to change. Okay. Nazarene, 3/7. So this one is irrational.
Oops. I was paying attention.
Wrong one. Yep.
Oh,
3/7.
rational. Irrational?
Do I have 2 integers? One on the top, one on the bottom? Is the bottom one 0? No.
Okay.
So it can be written as a ratio, right? It can be written as a fraction. So it is rational. anything that's rational, A over B, where B does not equal 0. Okay, so it's rational. Square root of 75, Nathan.
Irrational.
Irrational, perfect. Okay, Tadrian, 6 2/7.
Rational.
Rational, yep. We don't even have to, does it matter? Do we have to try to figure it out? No. If it has 2 integers, top, bottom, we're good. All right, Micah.
Rational.
Rational, because the 7 repeats, right? So even though it had 12.6 and then we got to the 7, once it got to the 7, it's repeating. It's not changing from that point. It is rational. Perfect. Okay, Nazarene, square root of 121. Rational. It's 11 times 11, right? So the answer is just 11. Nathan, 12 fifths.
Rational.
Rational. Perfect. Tadrian, pi.
Irrational.
Irrational. Perfect. Okay. So there's our quick review of what irrational and irrational look like. So when we are working in roots and they're asking is a root rational or irrational, if it solves all the way out to where it's just an integer, it's rational. Okay? If it has a root of anything left, it's irrational. Okay. Got it? Okay. So another thing, what we're going to look at today is we've looked at simplifying our roots, what that means, pulling them out, pulling out the indices. Now we're going to start adding, subtracting, multiplying, and dividing them. Okay? So, to think of it as what have we been working with? Just variables, correct? So we're going to go back and we're going to think of it in the same way as we would a variable. Let's look at addition and subtraction. Okay. I usually just write like that. Okay. If I have 3x plus 2x, can I add these?
Yes.
Why?
They have the same X thing.
Okay, so addition and subtraction, we talk about it, they have to be in the same family, right? 3 Davises plus 2 more Davises get in the car. I now have 5 Davises in the car, correct? They're the same family, so I can add and subtract them. When I move to multiplication, each one now stands on its own, correct? Because they're all connected by multiplication.
6x squared.
So now I have 6x squared. So now that they are multiplied, our family actually changes, right? So if you want to talk families, you have a husband and a wife and now you got a lot of kids, right? We've multiplied, right? It's not just people getting in the car, right? So addition and subtraction, the families have to stay the same. It doesn't change the family, right? Multiplication and division, our variable sections stand alone, and then they actually get changed a little bit, okay? Same thing with radicals, okay? When we are adding and subtracting radicals, we're going to work with the square root of 2. If we are adding and subtracting radicals, they have to be the same family. So what does our family look like now? Our family now looks like our root. Okay? So when the roots are the same, square root of 2, square root of 2, we can add the coefficients. What's really my coefficient right here?
2.
The number 1.
Oh, 1.
Right? So now I have 1 square root of 2 plus 3 square roots of 2. I get 4. This would be the same as 1x plus 3x would give me 4x. My variable is just my root there, okay? Addition and subtraction, we have to have the same root. Then you just combine the coefficients. Okay? We're gonna do some board races on those. Let me find my paper I wanted to do. Okay.
Relay, family
Okay,
versus.
so Tadrian and Nathan. Okay. You guys do this.
If it's raised too, can do it faster.
Wait, read.
What?
No.
Yes, correct? Correct. Is that a 9?
Yeah.
Yes.
He saw mine. No, he saw mine.
No, I didn't.
Yes, he did.
Okay, so tell me what you did.
Just added the thingies.
Okay, perfect. 7 plus 2. We don't change our root. Okay, perfect.
Thank you.
All right. Nazarene and Mikey, you're next.
Work on your nines.
It looks like a B. Like,
Looks like a backwards
yeah,
eight.
it looks good.
Okay.
I don't like writing on markers. Maybe just copy it.
Ooh.
I'm supposed to be the
No,
one.
Mike, it's,
No, I'm supposed to be the one copying off the B.
Okay.
and you almost did.
I was trying to, but you were going slow.
Okay. Excellent. Okay, so explain to me what you did.
Added the thingies.
Out of what thing?
Added the dirt.
Coefficient.
Coefficient. And then I just kept the square root because that's the.
Cube root.
Right.
Yep, so you kept it the same, so whatever it looked like.
Yes.
No, it doesn't.
Excellent. Same thing. So on this one, so it doesn't matter, this is where we've gotta start paying real close attention to what we have. It doesn't matter what our root is, right? As long as it's the same, it has to stay the same. And we just add the coefficients. Okay? I'm gonna put 4 up here, and then you guys can pick one.
You just like rush to the easiest. Rush to the easiest.
Whichever one's
Okay.
easier.
You don't know if that's the easiest.
Yep, teaching you that. Guys, they're easy.
Oh, it is actually.
Maxes are easy.
Okay,
Which one do you want? Harder or easier? Do you want hard?
That one's
one's-
zero. It's not
I
the
know.
same family.
So it's just.
Rational.
Oh, yeah.
here,
yeah,
you
yeah.
need a good marker?
I got one.
This one? Okay.
Wait. Oh, that's one. Okay, that's.
Don't
there.
second guess yourself.
Wait, no. This is like right here, right? It's
This,
not
this.
on this, right?
Correct, it's separate.
Yeah. So
Yeah,
it's
that's
this.
not 5 cubed.
Yeah, so it's this, right?
Yes.
Okay.
It's not 53 or 5.
It's not
yeah.
5 cubed.
Yeah, they didn't have.
No,
the
it would
thing.
have to be in a parentheses. Alright, so let's look at Nazarenes. 9, so the square root of 2, square root of 2 are the same. So it just stays, 9 minus 5 is 4. Perfect. Okay, cube root of 7, cube root of 7, they're the same, that's your x, that's your family. 17 plus 5, 22, excellent. Square root of 2, cube root of 2. Can you do anything to this?
No.
No. That's it. Perfect. Can't do anything.
Yay.
Square root of 2, square root of 2. There's our family. 8 plus 3 is 11. Excellent. Perfect. So addition, subtraction. Everybody got that?
Now
Nothing
on
changes.
multiplication.
What?
Now on to multiplication.
Multiplication. So let's look and see. So swap over on your review of radicals.
Oh, that. Oh.
What's the second page? What do you guys have? How much? No, this one. The
Oh.
not the irrational.
This one?
No, what's the second?
This one?
Okay. Skip that one. You guys can fill that one out on your end. I'll do that in a minute. Okay. Addition and subtraction. So at the top, like terms. Okay. Remember, in algebra, like terms are terms that contain the same variables raised to the same powers, right? So we were looking at x or x squared or x cubed, right? So you'd have to find ones that are like terms. So in the same way, the coefficients reflect the change when we have roots. The roots have to be the same index in radicand, okay? Radicand. But on this one, so we're just doing like terms. So it says simplify the following expressions by adding the like terms. Yep, perfect. 5x. Thank you, Nazarene. Nathan, do the next one. 5x squared minus 2x squared.
3x squared.
3x. Remember, your negative attitude has to go with x squared is your family. You have a 5 and you have a negative 2. 5 minus 2, 3. Perfect. Okay, Tadrian, 2x plus 4y.
That's 6x.
2x.
Wait.
It's not tricky. 2x plus 4.
You can't even add those. Can
You can't do anything. Perfect. You can't do anything. I have an X family and a Y family. They cannot combine. They cannot go in the same vehicle. Okay? Micah, 2x plus 3x squared.
Keep. Just same. Same.
Same. Can't do anything. This is not 5x cubed, right? Or 6x cubed. It's added.
Why is
Two.
it not 5x squared?
Because the first one's not squared.
Wait,
Oh.
can you add it with the
Yeah,
invisible
why
one?
can't you just put it together? Like-
Because this is the X family and this is the X squared family. And we are adding and subtracting. Now, 2x times 3x squared
Is 6x.
means, remember, because they're really all multiplied, so I get to commute them, and x squared is really x times x. So that's 6x cubed, but when we are adding and subtracting, they have to be the same. Same family. You are adding somebody to your vehicle. You're picking up somebody on the street. You can only pick up somebody who's in your family, right? Okay, that's the easiest way to think about it.
Don't want to pick up strangers.
Okay. So 4y plus y.
Why? Yeah.
Okay, this one, it doesn't have your coefficient. It's really the 1. 4 plus 1. The family is the y family. So we have 5y.
I almost bought all of these.
Yeah.
Well, all the last.
Okay. So, in the same way, for like expressions when we are dealing with radicals, we can combine them as long as, right? Let's do this one. I'll make it a 9. Your index and your radicand are the same. So this is our family. This is our new family. They have to be the same. So let's work. I'm going to put that big one up. And we're going to work it together. Everyone's going to come take a turn. 4 cube root of 3 plus 2. And they didn't even. Nazarene, come up and circle two that can be combined. Okay. Perfect. So when we combine those two, what do you get now? Write it with your blue marker. So combine those two terms.
Like, draw a.
No, just write what they are now. So you got 4 square root of 11 and 2 square root of 11.
Okay.
So now you have 6 square root of 11. Perfect. Okay. Nathan, come get 2 more. Use a different color, please.
So she knows who did what. If we mess up.
No, don't touch, bro.
One of the easy ones.
Perfect. Okay, Tadrian.
Just for you, Adrian.
I'll get you here in a minute. You
I
missed
knew he was
one.
gonna get mad.
You missed one.
No way.
Okay, hold on. I can't see.
No. Okay.
No, I marked them off to see. 'Cause
Okay.
All the sides.
I missed one? You messed up.
Okay. Those aren't the same.
Oh, wait. Is that added?
Oh, this
But that's cube root of 3 and that's cube root of 8.
Oh, okay.
So find the other one. There is one.
Wait.
Find the other one. Find the other cube root of 3 up there.
Oh, I can't.
Finances. Finances.
Wait, is it? Oh, it's this
Uh-huh,
way.
there it is. Yeah, cube root of 3. Cube root of 3. And the negative goes with it. Perfect. So what is this really? Minus, what's your coefficient there?
The negative one?
1. Perfect.
Is it a negative one, right?
Uh-huh.
Okay.
Okay. What is
Oh,
this?
Wait.
No, you.
Okay.
Positive or negative? Positive. Positive 4 minus 1 is a.
So wait, are these added?
Yes, it's all the same. Yep, there you go. All right. Micah, come up. What do you have left?
What colors? Purple.
Okay. Perfect. Perfect.
She made it sound like there's more. What in the world?
Okay. Okay. So he picked the square root of 3 family. He had a negative 4 and a negative 21. So so he has a negative 4 and a negative 21. Okay. They're the same, so we add them together and we keep the sign. So we've got a negative 25. Excellent. So then, what do we have left? We have
The 8 cube.
cube root of 4. Can we do anything with that?
Well, like, you can
Okay.
break it down.
And we have what?
That can become
A
2.
cube root of 8.
It can become
Could you break it?
Cube root of 8. 8 is a perfect
Two.
cube. That was on that list of things you should memorize at on the first page. The bottom.
2.
Perfect cube. What is the cube root of 8?
2.
2. 8 is 2 times 2 times 2. I need 3 of them. Do I have 3?
Yes.
Yes, so now I can reduce that to 2. And where does that get added?
Mine.
To 1.
Right there. So now I have 3. Okay, so we could combine those two. 1 plus 2 into 3. Okay? So your final answer, we're gonna would be this. So
Still looks hard.
we took the long ones, and we reduced it down here, okay? So you can write that underneath. If you didn't circle, I'm gonna leave these ones up, circle, underline, box. Here's an example. On mine, I will underline, circle the ones that match, box the ones that match, underline the ones that matched. So just make sure, whatever you wanna use, if you wanna use colored pencils, they're fantastic. I usually sit and do my math with colored pencils also. Or use circles, boxes, underlines, so that we can keep them all straight. Okay. We're gonna work the rest of these. Everybody got this one? Written down? Alright. Let's work through the next one. 4 cube root of 5 plus 2 cube root of 5 minus cube root of 5. Alright, who wants to do that one?
Me.
For Candy. Go, Nathan.
I want candy. That's what I heard. If he gets it wrong, can I correct it for candy?
Oh, no, we're gonna speak positive. When he gets it right,
When
he's
he
gonna
gets
get to pick.
When he gets it right and messes up, can I fix it out for candy?
Mine is speaking negative, so you can just check.
If, not when.
Wait, I forgot the little sign. Hang on, there has to be like a square. You're tricky.
No, it's not tricky. It's not too tricky.
So is it right?
Uh-huh.
Okay.
Excellent. Okay, explain what you did.
Messed up my brain.
You
Haha.
teach them what you did.
I added the thingies
Why did you add those two?
because it's the same family.
What is the family?
Knox family.
Cubed of 5,
Cube root of 5. Perfect.
and that's not the family.
And that's not the family, so it had to stay alone. Excellent. Very good. Pick something.
Hey, right here.
Okay. All right, who's doing this one?
I'll go.
All right.
I forgot what you were.
Okay, so I'm gonna have you just stand on the side, I'm gonna explain as we do this one, okay? First up, what is the problem? We have no families that look the same, correct? So the first step is to simplify all of your radicals.
By the way.
Yeah.
And 2. This
Perfect.
goes out to 3. Wait, is that part of that?
Yes, it is part of
Okay,
that.
then that would be 6, 2.
Okay,
This stays the same.
perfect.
2. And this goes in 4 and 2, which that goes 2, so 14. 2.
Okay, so back up. So in simplifying, we started over here with 18. 18 is 2 times 9. Remember? 9's a perfect square. We can think of it as 3 times 3. I need a set of 2. So he moved the 3 to the outside. But there was already a 2 there. So now what really looked like was 2 times 3 cube root of 18. All the numbers on the outside are just normal. We get to multiply them, okay? 2 times 3 is 6.
Well, it's not 18
Sorry.
anymore. It's
You're
2.
right. And we leave it. Okay? Square root of 2 stays the square root of 2. 8 is 2 times 4. 4 is 2 times 2. There's my set. that we moved to the outside. So this was 7 times 2 square root of 2, 14 square root of 2. Okay, so there's our simplification. We're going to go over some more with that. So now they're all the same root family, and you ended up with 14 plus 1 is 15, plus 6 is 21 square root of 2. Excellent.
She said you could get it.
You may get a
We
case.
use telepathy.
Okay, so let's do. You have this one written? Okay. Okay. Now so you can work this one. So there's two different ways that you can do this. You can either go ahead and combine anything that you see that you can combine, or we can simplify it all the way down and then start combining. So you can choose.
Can I not just,
You can simplify that one down. Yes, perfect. Excellent.
I don't know how to keep it, or like how to.
Okay, so now, perfect. The inside is 2 times 16. This is really a square root, right? It says I need 2 of the same numbers. Do you have anything that's 2 of the same numbers? Okay, how can you make it?
Oh.
Yes. Perfect. So now you have 2 of the same numbers, so we're gonna circle those and bring them to bring that number to the outside. So instead of square root of 32, what do you really have? 4. Your square root sign. And what's left? What's left over? Because you use those. 2. Perfect. So do the same thing to these. Let's simplify those.
Will it ever ask you to unsquare? Like do the 5 times 5 and then times it by 8? Like to put it back?
Put it back in.
Yeah.
You could, if you wanted to.
Will it ever ask you that though?
No.
Okay.
We want to go simpler, not harder.
Oh.
The goal is to always break it down, okay? So perfect. Where is your set of 2? We need a set of 2 to pull out. Okay, circle your set of 2, pull it to the outside. What's left over? Okay, and now this one is still multiplied by it, so we can't lose it. Because this is 5 times. Whenever it's butted up against it, it's times. So now it's 5 times, and this is just square root of 8 rewritten. Okay, so now on that one, okay, circle those, pull it to the outside. What's, yeah, so where did those go? Perfect. That was positive, and that was positive. So now what do you have here? 5 times 2 is 10. That just stays. Excellent. Perfect. 2 times 2 is 4. Excellent. So now they're all your radicals are all simplified down. So are they all the same family?
Yeah.
Okay, so when adding and subtracting, they have to be the same family. So you have perfect, perfect.
That was horrible. I wish I would've did it though, I'm like, ugh.
Okay, so let's keep going over those reminders of how we work that out. Square root of 64, when we're simplifying it, it's telling me I need to find how many of the same number? 2. 8 times 8, there's 2. When we bring this to the outside, we're only bringing the one digit. I know I have a group of 8. Okay? If there was already a number out here, we can think of it in parentheses. You're welcome to write it in parentheses if you want to. So my 5 would stay, my square root of 64 is 8. It stays, so now my new number is 40. Okay, so the number one mistake as we work through these is to lose our coefficients that were up there, or to not multiply them as we work down. So just a reminder, as Nazarene worked through this, 8, the square root of 8 is rewritten as 2 square roots of 2. That's all by itself. She had a 5 in front of it. Anything once it's in the front is fair game. It's just like a normal multiplication problem. Okay, this would be the same as then putting, remember we can replace that as x. So if you want to think of that as 5 times 2x, that would be 10x, correct? We multiply our integers, we leave the rest. Okay, let's work that next example. I give you these sheets with these examples so that you can use them to see the steps. When you have tests and homeworks and stuff, these are fair game. You can use these, okay? For the steps to go through. Because they're just showing you the steps, okay? Let's work through this one. Come on, Tadrian. We're combining all of the things that we were learning about simplifying with writing. Come on, you got it. Come on.
7. My hint is 7.
All right.
3.
First step. These are all really big numbers, right? So we want to simplify it. Down? Okay. So, how are we going to start? Square root of 147.
3's the
Okay. Calculators. You need a calculator?
Probably.
Okay. 3 times what? 147 is 3 times 49. So write that under there. 3 times 49. Perfect. 192 divided by 3 is 3 times 64. 75 is 3 times what? You should know that one. You have quarters. 75 cents. 3 times 25. Good. Now, because this is really square roots, we're looking for perfect squares, right? In this first one, do you have a perfect square?
Maybe.
What are our perfect squares?
Okay.
Multiplication. So 2 times 2 is 4. 3 times 3 is 9.
So now,
16. Let's think. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. Okay. So we're going to do 7 times 7. Okay. There's your double. So it gets moved to the outside. Nope. It doesn't go up there.
no, wait.
So it gets moved. Yep. It gets moved to the outside of your radical.
Yeah, so it's right here.
7. And what's left on the inside? We've used this up now. 3.
3. But there's a, never mind.
Okay. So we're gonna write your radical. There you go. So on this one, the 64, 8 times 8 is 64. Awesome. Okay. Do you have a group of 2? Okay. Circle it. Move it to the outside. What's left in the middle? There you go. Yes, perfect.
You got one of them right.
Perfect, move it to the outside. And then we're just bring this one down. Now, we have to go back and ask ourselves, we're adding and subtracting, are they the same family? Yes. So our family stays the same, so immediately you can write the family down. So what family are you working in?
Addition.
No, what?
Oh,
What radical family do we have?
okay.
Okay,
Square root 3.
square root of 3. Perfect.
You add together.
And then what do you do with all those other numbers? Add or subtract, yep, whatever they are.
Mrs. Thomas. Mrs. Thomas.
Yes.
I'm
Can I?
the two.
Oh, yeah, you missed this
It
part.
took 3 years.
Oh, wait, what did I miss?
Okay,
Oh, the one, two.
so on this one, we have 8 cube root of 3, but then what happens here?
Mike, you should have said that.
I was tired.
16, perfect. I was just looking back there, I was like, wait, we really gotta go back to 6. Perfect, let's not lose it. Like I said, that's our number one mistake.
His pink shirt's in front. I can't see.
Same.
Oh,
No problem, my
peak
shirt.
shirt.
So we have
Oh.
7. Okay, so do you see what we did here? Do you see what we did there, Nathan?
Yes. Many times by 2? Yeah, yeah.
So 192 was rewritten as 8 square root of 3, but we had this whole thing times 2 because we already had 2 of them. So we ended up with 16. And you got 24. Let's see, 7 plus 16,
23.
25.
23.
Yeah, it should be,
23?
sorry, 23 plus
That's
5
right.
minus 4.
Wait.
Yep, so this is 1.
Wait,
Is that right?
7
Wait,
plus
what's one?
16.
Minus 4 plus 5 should be 23, right?
24.
I have 24.
24.
Yeah.
24.
Stage room's right.
I think
right
so.
or wrong?
7
Yeah.
plus 16.
You're right.
Good job, Tajian.
Yeah.
Yeah.
24.
Okay,
Yep.
so
Perfect.
That was the answer sheet and it said that. Stop looking at the answer.
Okay.
Answers.
So rules for adding and subtracting radicals, we're gonna simplify them first, right? Make sure we get to the families. Alright, we've got adding and subtracting. Can we move on to multiplication and division?
Yes.
Okay, now, multiplication and division, where adding and subtracting have to be the exact same family. Multiplication and division have to be the exact same index only. Okay, so what part is our index?
The top thing. The little tiny root.
The 3 or the 9?
3.
3. Okay. So if you think about this, we either have to be finding cubes or finding squares. We can't combine those, or fourths or fifths or sevenths or whatever we're doing. Okay. So when we are doing multiplication and division, we have to have the same index. Okay. We have to be working within the same question of, I need 3 groups, I need 3 groups. Okay? So, the expression for multiplication and division, if we're going to look at our little variable, a to the b root of c, I'm going to write it like this, okay, times d to the b root of e. We're looking, we've got the same indexes, correct? B, so whatever that is. So in the same way as we do the commutative property with multiplication, division, we're going to do it here. Our outside ones get multiplied, a times d. Okay. Our index root stays the same, b root of, and then our inside ones get multiplied, c times e.
That's not terrible.
No.
Until
Yay! That's not terrible.
until it gets really really.
Until you
complicated.
add like
Okay.
all these extra.
So the outsides get multiplied, the insides get multiplied, and they stay under the same root.
What if the roots aren't the same?
If the roots are not the same, you cannot, like if the indexes are the same, you cannot multiply them
They're
together.
right.
Okay.
Okay?
Can you multiply the A and D?
No,
Hadrian has
can't do
questions.
anything because this is connected.
Okay.
Ms. Thomas.
No.
Hadrian has a question.
Hadrian has a
Wait, are
question.
they gonna start putting exponents inside
Sometimes, yes. But remember, these are all just building blocks. So if you have a giant, you know, you get Legos. We just got the Sydney Opera House Lego set. You know, so there's 3,700 pieces in it. Okay.
That's a good number.
And so you get that, and you're like, "Wah!" What do? Start with the first building block, right? So the building blocks are not changing on any of this. We're just combining them. We're making a bigger structure.
Aluminum Falcon.
But all the things are still exactly the same, okay? So let's look at this first one. So we're gonna practice this first one. 3 cube root of 2. Do they have that written down on your paper?
Yes.
3 cube root of 4.
3 times is 3 and 5, right?
So if this was addition and subtraction, you couldn't do anything to it, correct? It would just have to stay. However, it's multiplication and division. So all of my numbers, I told you wrong, Nazarene, yes, you can combine them. All your numbers on the outside stay. Because everything on the outside, remember we can rearrange this by that commutative property of multiplication. We can rewrite it, right? They can move all around because they're really all just multiplied together. So all of my numbers on my coefficients on the outside get multiplied. So we have 3 times 5 is
15.
15. Okay, are my indices the same?
Yes.
Yes. So I stay cube root.
8.
8.
8.
2 times 4
Wait,
goes
so
good.
does that mean it turns into 2?
Now,
Yeah,
this
2.
turns into a 2, and my answer is
30.
30. Come get an extra one.
Oh, yeah.
Sure.
Okay, is this rational or irrational?
Should last one.
Rational, because,
It can be a regular.
yeah, it's just a regular number. Simple. Perfect.
See, it's not bad until you like
They can't
Make it
add.
bad.
Until
They make it bad.
Okay, let's work this next one. -2.
Oh, I wrote it on
So it was 2.
Okay,
Oh, sorry.
what is my index here?
2.
1. Or 2.
2. It's not shown, so it's 2. So is it the same?
Yeah.
Okay, so I can just go ahead and put it there. Now, what 2 numbers get multiplied on the outside?
-2 and 6.
-2 and 6, so I end up with
-12.
-12. All right, Tadrian, what 2 numbers get multiplied on the inside?
22
22
and 4.
and 4, so get 88. Which is what? 22 times 4. That was kind of a tricky one in the first place. Do I have anything that I can pull out?
2.
I could have gone ahead and just reduced this in the first place, right?
Do you have to do that, or you can just leave it like it is?
It would be easier.
No, you need to simplify it.
Okay.
So I'd pull this 2 out.
Oh, wait.
What happens to the -12?
Times by 2.
It
4.
stays
Wait, times by 2.
times 2, square root of 22. So now I ended up with -24, square root of 22. Had at the beginning you said, wait, hold on, square root of 4 I know is 2. So this is really this whole thing times
12 times
12.
-2.
Then all you'd have to do is multiply
-24.
your integers there, right? Yep, -24, 2 square roots of. Now, is this rational or irrational?
Irrational.
Irrational because
It's
That
not-
22.
It's not a perfect square.
You can't do anything with that. You ended up with a radical. If your radical is left, it's irrational.
Can I try the next
They're
one?
made like that.
We can estimate that value. Type it into your calculator. You can approximate it. But would we ever say this equals? Would we say that?
Is that the real answer?
Mhm.
Oh, maybe.
Would we say that equals that? Would we ever write this sign?
No.
No, because it's like, it's close, it's iffy.
You do a squiggly
So our equal sign needs to be iffy. It's almost there.
Raise your hand. Oh my goodness.
Guys got that one?
Hands here.
Did we go over the real world application for this yet? Are we still getting to that?
We're still getting that. No. You stay in here and you stay engaged and you'll get your bread at the end. All right.
That's the
Let's
real
do
world
one more.
application. You learn
Okay.
this, you get bread.
Okay.
Can I do this one?
Yes. Come to the board.
You ran out of Starburst.
Sorry.
No more
Jolly,
candy.
Jolly Ranchers now.
Very well, sure.
Oh my goodness. I'm restarting. I saw something.
Okay.
And it's 2 and 2. And you times that by 2.
Mm-hmm.
6. 3.
Okay.
Whoa, oh,
But then you have to do that.
That's fine. No, you can't do
No, you
that
can't
one.
do anything.
But then it doesn't have to see.
Then
Oh
you
wait, it's multiplying.
It's
it doesn't matter.
multiplying.
So then this times that is 12
Okay.
and then 36. I don't know. I have no idea what I'm doing.
18.
18.
Now can you simplify it?
Half of 36.
No, don't listen to him.
You just said 36.
And this is 3.
Okay.
Times that by 3.
Yes.
Then it's. Oh my god. 36. 2.
Perfect.
It is 36. You accidentally got the answer.
No, we didn't. You got it for reals. Okay, so you could have just done 6 times 12 and gotten what? 6
72.
square root of 72, right?
That's a big number though.
It's a big number, right? And then done, this is 2 times 36. Well, there's my 6,
oh, I'm doing that.
right? So I have 6 times 6 square root of 2. 36 square root of 2.
I was gonna get to there.
Yes, I like that you did it the other way. Because sometimes you do something and you're like, oh yeah, I see backwards, I could have done that differently. Or you could simplify it exactly how Nathan did. Excellent. Okay, so now, what do you think this means to division?
I think you just don't do it. That means 1/3.
Okay. Close. Okay,
Wait, he's wrong?
It's something over 3.
yes. Okay, so if you have radicals that are being divided, as long as your indexes are the same, what did we do over here?
We multiplied.
Oh, 3 divided by 9?
What did we do here? We left our radical with our index the same and we
Multiplied.
combined this underneath the radical, right? Right? If it was underneath, it had to stay underneath. So what do you think that means
They
for
combine.
division?
They combine.
If they're the same, if they're underneath, they can stay underneath but combine. So square root of 3 over the square root of 9 is the same as the square root of 3 over 9,
Or 1/3.
which is the square root of 1/3.
So Mike got it right.
I just forgot the little square root part.
Oh, but it matters. Square root matters. Okay. So, Tadrian, we're taking what we knew about multiplication. when our indices are the same, we can combine our numbers underneath the radical, right? And just multiply them together. Same thing for division. When your indices are the same and they're divided, you can just combine them underneath the radical. Okay? So if I have and your teaching textbooks teaches it backwards, it teaches the multiplication and division first, and then the other one second. But it's fine. Let's do square root of 14 over the square root of 7. How would we read? Nazarene, go rewrite that.
What lessons are we doing this week?
I'll see you in a minute. Perfect. Square root of 2. Excellent. So she rewrote them both underneath. Solved underneath. Then if this ends up being an answer that you can simplify more, then you need to simplify it. So if this ended up being the square root of 4, then you would write the answer within B. 2, right? You just keep simplifying down. Okay, perfect. So if you have, so then let's look at, so everyone got that? You're just doing division. You're just rearranging it, basic division, okay? Now, in the same way that you can combine them, you can also do what? You can break them back up, okay? So if I have the square root of 1 over 9, it means square root of 1 over square root of 9. Okay? What's the square root of 1? 1. What's the square root of 9?
9. 3. That's what I meant.
3.
I was
Okay,
just resetting.
9 is 3 times 3. There's my double set. I bring it to the outside. So sometimes it might be beneficial to break it back up. Because you're like, hey, I know that's an answer. That's a rational number. Right? So we can end up with a rational answer at the end. Does that make sense?
That's a rational factor.
Yeah, so the square root of 1/9 is 1/3.
I thought it's 0.3.
Yeah, but it repeats.
Oh.
Remember, as long as it's repeating,
Oh, yeah.
terminating or repeating decimals. Remember, what does a rational number mean? It simply means it can be written as a ratio. Right? An integer over an integer as long as the bottom's not 1. Is 1 an integer? 3 an integer? Yes. Is the bottom number 0? No. So you're good. So let's look at square root of 10 over the square root of 2. How would we rewrite that?
Square root of 10 over 2.
10 halves.
Okay, which equals
5.
square root of 5. Excellent. Okay, so basic multiplication and division, we're just putting them inside roots. Okay? You guys have a paper this week to work through. This is one of the problems from it. Square root of 9 over 64.
Ooh, what do
What should we do? Should we leave this one underneath the radical?
Put them up.
Split it up. So I would split it up as a square root of 9 over the square root of 64.
8.
What?
3/8.
Square root of 9 is 3. Square root of 64 is 8. 3/8. root of 8 times the square root of 2 plus the square root of 3. Can I add square root of 2 and square root of 3?
No.
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 Because for addition and subtraction, the entire thing has to be the same family. Is this the same family? The indices are the same, but the radicand is not. Not the same family. Okay. But what can we do?
Distribute.
We can distribute. So the square root of 8 times the square root of 2 gives me what?
16.
Square root of 16.
Which can go to 4.
And I'm going to add square root of 8 times the square root of 3.
24.
24. Remember, our indices are the same, so we can multiply these. So we're just multiplying the numbers underneath. The first one is 4. Right? Square root of 16 is 4. 24 is
5. No. 4 and 6.
4. Yep, 4 times 6. So I've got 2 square root of 6. Can I go past that? No. I'm adding.
Oh, you are.
They have to have the same families. This would be the same as 4 plus 2x. Can I go anywhere with that? Nope. So there's your answer. Yes, sir.
What if in the parentheses, one of them is like to the third? Can you distribute property?
If it was this,
Yes. Can you distribute property
No.
still? No? Okay.
no. Because the rule for multiplication is that your indices have to be the same. Okay? So a square root of 8 cannot be multiplied times a cube root.
So can you even solve it?
It would just be get written out like this would be the same as an x and this would be like a y. You know, so when you end up like 2xy, so they would just go next to each other. You don't have any like that on this work. Okay, let's do one more here. Adrian, can we do this one? Since you're packed up, ready to go.
Knox is packed up too.
Come on. We've got, what, 7 minutes left? 55? Isn't that right?
Yep.
Pick one.
So what am I doing with this?
So you're wanting to simplify this. So what is it telling us we need?
Just 3 of each?
3 of each. So we cannot exchange anything from the inside to the outside without having an exchange rate of 3. We need 3 of them. So what can you pull out?
So is this x times x times x?
Right? Remember, what do our exponents mean? Okay. So there's a set of 3. It gets. Just put it down here. Nope.
Oh wait,
it's not times
that's
3.
the little.
That's
okay.
the indices. Yep.
Okay, and then. Go. I'll have to do it all right.
So remember what was our, no, you don't have to write them out. So remember, what were we looking at? If you're looking at big numbers like this, let's think through practically, problem solving. What would be, I need groups of 3. What mathematical problem, addition, subtraction, multiplication, or division, gives me groups?
Multiplication. Division.
Multiplication and division give me groups, right? So I have something and I want to break it up into groups. You would divide. So I've got 3x cubed and I need 3 of them. So 3 divided by 3 is 1. So I'm going to end up with 1 of them pulled out. Okay? That makes it.
5 numbers instead. Like,
3
just,
divided by 9 is 3.
So in the y's.
So you put 3.
So this is what Tadrian said. He was like, I don't want to write out 9 y's. I'm going to do 9 y's like that, right? There's 9 y's.
Why?
There's a set of 3 that gets pulled out. Here's another set of 3 that gets pulled out. There's another set of 3 that gets pulled out. So now how many Y's do I end up with? 3 Y's. Okay, now so do your Z's. Yeah.
Z squared, right?
Yes, exactly, perfect. Z squared. So you can think of it in terms of, I've got 6 Z's, I've got 2 sets of them, I pull out 1 Z, pull out another Z, end up with Z squared, or I have 6 of them, I need groups of 3, 6 divided by 3 is gonna give me 2, okay? So those are those little shortcut things that you can think about. Okay, we have 5 minutes. I'm gonna pass out red and you guys are gonna play a game of tic-tac-toe for rational and irrational numbers. You can divide up into pairs.